example. The Collatz conjecture. Why it is? Well, let me tell you, because it's pretty cool. So, to start with the Collatz conjecture, we gotta first know these two pretty simple rules. Okay, for any integer, which we're gonna call x sub 0, if x is odd, then the next x1 equals x0 over 2, and if x is even, then x sub 1 is 3x0 plus 1. And then repeat until x of n equals 1. So, let's say if we get x1 that's not equal to 1, then we go on and we start that, we calculate x2 using the same set of rules, and then we just keep going until we break down to 1. For example, let's say we have 20 here. I have the steps on here, but I'm also just gonna do it on this whiteboard. So 20 is even, so we follow the half rule, which brings it down to 10. 10 is also even, so we follow the half rule, bringing it down to 5. 5 is odd, so that brings it back up to 16. And 16 breaks down to 8 because it's even, to 4, to 2, to 1. I hope you can see that. I think she said it. Yeah, so that's done in 7 steps. And that's pretty cool. And then, if you want to look at a lot of numbers, you probably can't see this too well, but you'll see here there's a bunch of different numbers and how they break down. They all go to 1. So, the blacks are the even numbers, the blue ones or the purple ones, they're the odd numbers. And then the orange ones are the powers of 2. And actually, because of the way the rules are, every single every single power of 2 breaks down into whatever the power is. So for 2 to the n, it breaks down n steps. So like 64, which is 2 to the 5, that breaks down to 1, 2, 3, 4, 5, 6. 64, which is 2 to the 6. Wait. Oh yeah, 64 is 2 to the 6. Breaks down in 6 steps. I don't know why I thought it was 1, I'm being silly. And then here's some really pretty, cool looking visualizations. I think these are pretty big numbers. And I don't know exactly how they figure how this works. Those are pretty cool. This one, I'm gonna guess that it sets numbers up in a kind of curvy way, but I'm also not sure exactly how it works. Oh wait, no, because look at this. So these are just a bunch of different starting numbers, and then they just tilt it as they go further and further. And you can see this must be the higher. Well, this must be the powers of 2 right here. This, I don't know what that would be. I don't know. These are just all the different steps that I can take with all these different numbers. I don't know, I think the visualization of this is really cool. But we just stated the kind of these rules, we haven't actually said what the actual conjecture is. So the conjecture itself is this. Oh shoot, not 0, pretend that says 1. So for any positive integer x, following those rules will eventually go to 1. 1, that says 1, not 0, you're just crazy. Okay. However, this is actually unproven. So we've tested using computers up to 2 to the power of 58, which is that number. Let's see, 1,000, million, billion, trillion, quadrillion, 288 quadrillion, 230 trillion, 376 billion, 151 million, 711,744. So we've tested up to that high using computers. Any one trivial is any one number is pretty trivial, but I tried to run it to this on my computer overnight last night, and it maybe got to 8 digits, so like here, yeah, it maybe got to around here. So it would have had to do that times this more. So like if you do it on a big computer, like a supercomputer, then I could do it like we have a supercomputer here at the, where I go to university. If I ran it on that, it could probably run to this in a couple days. Yeah, that's how big this is. I don't know. I don't really know how fast the supercomputer is compared to a regular computer. And that was just my laptop. If I ran it on my actual computer, I could probably do this in a year. I'm not even kidding. It might legitimately take that long. I don't know though. I don't know the difference in the speeds. I don't know what can cause the difference in the speeds because I'm not a CS major. Well, I guess that would need to be CE too, either too. So why it's cool? I mean, so it's cool because it's math, and math is cool. But like, it's a couple of very basic functions. If you don't know what the mod function is, it's basically, you know, you divide, so let's say like 36 over 13, right? That is 6. That's 2 equals 2 plus, you know, 10/13. So then 10 would be the mod. That would be 36 mod 13. So it's just finding the remainder of integer of division. I guess it doesn't have to be an integer. This number has to be an integer, but this one I guess wouldn't have to be. So using mod 2, it just tells you if it's even or odd, depending on if it's a 0, which means even, or odd, which means 1. And then it just uses 2, you know, very basic arithmetic functions. And it gets you this, which we don't know, you know? And that's crazy, because like, it's been around since 1937. That is, I looked it up, 85 years. And I mean, I'm assuming it's actually like 84 and change. I didn't look up the exact day because you know, these things are made up in some mathematician's lab and they work on them and they might not even tell anyone about it. But 18, and I tried, yeah, let me go back. I actually then after this, I tried messing around with some of these numbers, making this 4, making this -1, and those all get caught in a loop eventually. I think it was at like 3 for negative, but if I did, meh. I would do like x and over 2 or 3x and -1, not x to the n, but xn, you know. And I start with like 4. No, it wasn't 4, it was 3. Why is this going down? Okay. I did it with 3. No, that's 9, that's 8. That would also collapse down to 1. Okay, as I was saying, if I did it with 5, that would give me 5 times 3 is 15, 14. Go down to 17. I'm still doing it, go down to 7, which would then which would then 21 minus 1, that's 20. 20, which goes to 10, which goes back up to 5. So like this one has a loop already. 4 also had a loop. But yeah, so these will loop otherwise, but we can't find a loop for specifically 3x to the n plus 1. And that's I don't know. The fact that it's so unique, and the fact that we've never been able to actually mathematically prove it, even though we checked super crazy far, it's just so cool to me. I don't know, I'm a nerd, so, but it's just like how we have not been able to figure out, like we figured out calculus, but this very simple arithmetic thing, no one can figure out. You know, because it's like, all we need is one counterexample for it to be wrong. Although I guess there would actually need a couple, you would need at least 2 numbers that somehow oscillate back and forth, which couldn't happen, because I think it is proven for, it is proven for all even numbers, I think. I might be wrong about that, but I know for sure it's not proven for odd numbers. That's just crazy. I guess though, if it's not proven for odd numbers, it couldn't be proven for even numbers, because every single odd number has, you can do 2 times that and then get that even number, and then it breaks down back into that odd number. So it would not be proven for even numbers, so I'm wrong, crazy. It is proven for all powers of 2, because you just keep dividing 2 until you get to 1. I don't know, man, it's just so cool. And I made this presentation just to talk about a stupid little math thing that I think is cool. Because math is so cool. I'm a nerd. Yeah. And I can always make more of these because I like talking about nothing math. Alright, bye. To the random person who found this on YouTube, L.